Okay, Matty, let's go again then, see if we can sort this out. So we'll start with glycolysis. So this is occurring in the cytoplasm of the cell. Okay, and we're starting with glucose as our hexose sugar. So it's got 6 carbons. Okay, the first thing that occurs here is that we get a phosphorylation happening. So glucose becomes glucose phosphate, but it still has 6 carbons in it. And this phosphorylation increases the energy of the molecule, and it also means that you're increasing the negative charge, so it keeps the glucose actually in the cell. Okay, and you've been told now that the enzyme is a hexokinase enzyme, and again that will have allosteric regulation. So if there's lots of glucose in the system, then that's going to activate the hexokinase, and if there's lots of glucose phosphate in the system, that's going to be what we called end product inhibition. So you get end product inhibition here, end product inhibition, to prevent that enzyme working. Alright, so from glucose phosphate we then do an isomerization to fructose phosphate, and it gives you, I think in the anaerobic notes, it gives you all of the details of that. But basically you just need to use an isomerase. Okay, and then we need to phosphorylate this again to make it fructose biphosphate. And you probably need to know the enzyme there. Let me get my notes that I took earlier. It's phosphofructokinase. Okay, so phosphofructokinase. So again, you need to just refresh yourself about allosteric activators and inhibitors here. So the inhibitors, which are the minus ones here, are ATP. So if you've got enough ATP in the system, you don't need to make any more. So that's going to stop this enzyme working. And citrate, which is the first product of the citric acid cycle. So if you've got enough of those, then you don't need this reaction to happen. But if you've got lots of AMP in the system, then that will activate this enzyme. And if you've got lots of fructose biphosphate, then you will also activate the system and drive it forward. Okay, now you've got this 6 carbon phosphorylated sugar, biphosphorylated sugar. You can then split it, so you're doing the splitting, the lysis of glycolysis here. And you've got glyceraldehyde phosphate, okay, which is 3 carbon because it's half of 6. And you've got the other isomer, which is dihydroxy acetone phosphate, which presumably is allowed into the mitochondria through the first membrane anyway. But then you have this isomerase at A level you did, isomerase, to turn it into that dihydroxyacetone into glyceraldehyde. So now from here on in we go everything twice, and I'm hoping that as I move this screen up that it gets captured on the video. So let's have a look at what happens to glyceraldehyde phosphate. Well, we need some inorganic phosphate coming in here, so it's not coming from ATP. Oh, and I've forgotten that. Dearie. Okay, so the phosphate here to add onto the glucose comes from ATP here, which is daft because we're supposed to be using respiration 4 to make ATP, but actually we're using some up. And again here to phosphorylate your fructose phosphate, we need some ATP. So we've already used 2 ATP. Alright, but at this point here, you don't use ATP to add the phosphates. You just use inorganic phosphate. And you make glycerate biphosphate, or bisphosphate, or diphosphate. The bis, bi, or the di, what is it? It's the carbon that you're attaching the phosphate group that determines whether it's biphosphate or diphosphate, but this is glycerate biphosphate. Now, when you change glyceraldehyde phosphate to glycerate biphosphate, as well as phosphorylating, so this is phosphorylating when you're adding phosphate, you will also dehydrogenate your glyceraldehyde phosphate. So you'll have dehydrogenase enzymes working here, stripping off hydrogen from the glyceraldehyde phosphate. So dehydrogenase enzymes will be working to remove the hydrogen. And the molecule that they put them onto is an NAD molecule. So you'll have oxidized NAD in the cytoplasm. You'll allow it to pick up the 2 hydrogens that are stripped off glyceraldehyde phosphate, and that produces NADH plus a proton. And because you're doing it twice, okay, it's 2 of that, actually 4 of that, okay, and 2 of that. Alright, so let's move on then to what happens to glycerate biphosphate. So now we can start getting back our ATP. So glycerate biphosphate just becomes glycerate phosphate, and we need to have 2 in front of that and a 2 in front of that. And then what comes off here is obviously phosphate, and we can use it to add it to ATP to make 2 ATP. So we've already recouped the ATP we used earlier. And then finally we go to pyruvate. That's our final end product for glycolysis. And again, we're taking off that phosphate so we can phosphorylate 2 lots of ATP into 2 ATP. So what we have is 4 ATP that we've made, minus the 2 ATP that we used above. So that's a net of 2 ATP. But we've also got 2 lots of reduced NAD, which will then have to get transported by the more involved mechanisms that you're learning about into the matrix. So it won't be in this form, but something will happen to take those hydrogens off there and take those through into the matrix so they can be used to create ATP. And you've also got 2 pyruvate that can go into your link reaction. Okay, so I'm going to stop there and see if that works.